So till now we were looking, we got to know about the binary search tree. So binary search tree is nothing but the elements in the left subtree is lesser than the root, and root is lesser than the right subtree. So these are some basic terminologies, and these are the operations of basic binary search tree. So moving on to the first operation, first we have to create a node using the structure node and allocate the dynamic memory allocation using the new operator. So this is the insertion operator. What we have to do is, first we have to create one operation, insert data. Then first we have to check, when node is created, then we have to check whether that root node is equal to null. If it is null, we have to return that particular root node. If it is not null, what we have to do is, we have to insert, first we have to check the left, whether the data which you are inserting is less than the root. If it is there, then you have to insert that particular data onto the left subtree. If at all it is greater than the root, then we have to insert that data into the right subtree. So that is what, then we have to return the node. So while inserting a node into the binary search tree, you have to see to that it is placed properly. That is, you have to follow the property of BST. That is, the element, data element, or insert the data which you are inserting is less than the root. If it is less than the root, insert it in the left side. If it is greater than the root, insert it in the right side. So by doing that, you are not violating any binary search tree property. Okay. Now, this is the insertion operation. Can you see here? So, if I suppose this diagram, I already have a tree with 3 nodes. Now, I want to insert this 8. So, if I want to insert this 8, I have to check. First, I will be checking this, comparing the 8 with 5. It is greater. So, if it is greater, what you have to do is, I have to insert it into the right subtree. Now, there is already one element in right subtree, that is 7. I am comparing this 8 with 7 now. Now 8 is again greater than 7, so I cannot insert into the left subtree. So I have to insert it into the right subtree. So I am inserting 8 here. Okay. Now if I want one more example, this is one example. If I want to insert a minimum value, what am I supposed to do? I have to check this data element with the root. So 3 is lesser than 5. So what I have to do, I cannot insert it to the right subtree, I have to insert it to the left subtree. So I will check with this. Now coming here, I will check whether 3 is right. In right there is already one element, 1 is there. Now again I am checking this one with 3. So 3 is greater than 1. So if it is greater than the root, what am I supposed to do? I have to insert it to the right side. So this is insertion. While inserting an element, you have to keep in mind that the data element which you are inserting should be compared with the root element. If it is lesser, you have to insert it to the left subtree. If it is greater, you have to insert it to the right subtree. So this is the insertion operation in a binary search tree. Okay, this is creation of a tree node using the class. So class node, public, then I am creating one data using integer data type, then one left pointer, then right pointer. After this, I am going to put this data as a, creating this data as a null. So the root data will be null. So this is creation of a tree node using class. So this is the implementation part of that insertion operation. So see, I have already created one node, insert operation. So one root node is created and one data for the integer. Then if I am checking whether the root node is equal to null. If the root node is null, I am going to return that particular root node. Okay. Else, if the root node is not null, if there is an element in the root node, I am going to come here. So once I come here, I am going to check whether the data I am going to insert is greater than the data which is already there in the root node. So that is data is less than or equal to root data. So I am checking this data whether it is less than or equal to root data. If it is less, then I am going to insert that particular current node into the left side of the binary search tree, or else I am making this root left as the current node. After this, if this is not correct, if the data which I am inserting is greater than the root, I am going to insert that particular root to the right subtree. So I'm inserting the data, I'm making the right subtree as the current node. This is the insertion operation. Once this is done, I'm going back to the root. This is the implementation of the insertion operation of a binary search tree. Now, the next operation is a deletion operation. So actually there are three methods to delete an item from the binary search tree. So let's see one by one. So when the node is a leaf node, that means when a binary tree, whatever element I want to delete is just a single leaf. It should not be branching out. Now, which are the leaf node in this diagram? So 1, 4 and 7 are the leaf nodes. So what am I supposed to do? I can delete any one of this because it is a leaf node. I can delete 1, I can delete 4 and I want to delete 7. Now I want to delete 4. So if I am supposed to delete the 4, what I can do is I can just remove this edge over here. This can be removed directly. Just by removing that, the connection, the edge will be lost. The data element also becomes lost. So if there is only leaf node which you have to do it, you can directly do it by just deleting the edge of that particular node. So it is easier to delete an element in a binary search tree if it is a leaf node. That means it does not have any children. Okay, this is the first condition. The next condition is when the node has only one child. Now what I am doing, see here. So this 5 has 3 and 1 and 5 has 7. So which is the element which has a one child is 3. If I want to delete 3, what I am doing is I am going to shift this 1. This element is being replaced by this particular. I will replace this element till here. So 1 will be placed on to the 3 position and I can delete the element. Okay, this is what happens when a root node, when whatever the node has one child. If there is a one child, I have to replace that particular child to that particular node and then delete the node. This is the second option when a node has only one child. The third is when the node has two children. There are two possibilities in this. The first possibility is if the node to be deleted has two children, then we find the in-order successor for the node and then copy the in-order successor to the node. Later we delete the in-order successor. What I am doing, see here, there are 6, 4, 2, 7, 9 and 11. I want to delete 6 which is in the root node. So what I am doing is I am comparing 6 with the left, that is in order, right subtree. So 6 is greater than 4, so I cannot go to the left side. 6 is greater than 2, I cannot go to the left. So what I am doing is I will start comparing this with the right subtree, that is 6 is compared with 9, 6 is compared with 7, 6 is compared with 11. So I will move to this part because the elements which are there, this root element is lesser when compared to all the elements in the right subtree. So if I want to replace this, first before removing this, I want to replace it with some node. Because if I just deleted the complete whole branch, this whole right subtree will get lost. So just to avoid that, I will replace this 6 by some minimum value. What I am going to do is identify some minimum value in the right subtree. The minimum value will be 7, 9 or 11. So 6 is nearer to 7. So what I am going to do is I am going to replace 6 by 7. After that I will be deleting 6. So it says in the about tree to delete the node 6 with 2 children, we first find the in-order successor for that node to be deleted. We find the in-order successor by finding the minimum value in the right subtree in above case. The minimum value is 7, then the right subtree we copy to the node and delete the in-order successor. So that is what you have to identify a minimum value which is there in the right subtree, replace it with that particular element and then delete the in-order successor. This is one way of doing it. Okay, so now the next way is identifying a maximum value in the left subtree. If at all 6 is, now 6 is greater than 4, we will move to this and we will identify the greater number which is there in the left subtree and replace it with that. Okay, that is one more option. So these are 3 methods to delete the element from the BST. Okay, this is the implementation part. So here what we are doing, if a node is leaf, then delete the leaf. So if a node is a leaf node, it means it does not have any link to any other data. So there is only one single leaf node. Then you can directly delete it. So it says if root is equal to null. The first condition is you're going to check whether the root is null. If it is null, return the root. So there is no elements inside, only one element is there. So you're going to return the root. Next condition, if root data is greater than key, if the key element, so whatever the element you want to delete, if it is greater, what you are going to do is, I am going to delete the roots subtree. I am going to delete the root. If it is greater than the root, the subtree, what I am going to do is, I am going to delete the nodes which is there towards the left. Okay. So else, sorry. If this is not, condition is not true, I will go and check, I will delete the right part of the tree. Okay. So the next is, if one of the children is empty, that is only one side if it is there, I am going to say node temp. I am going to create one node which is temporary, which is equal to the right node, and delete the root and return temp if there is only one. Okay. After this, moving on to the next part. See, if the children exist, then we delete the node plus that is what. If at all we have children, two children to one particular node, how to delete it? So first of all, how do you do it? You will be identifying the in order successor, compare it with the left or the right side or the left side, find the maximum minimum value if it is in the right side, maximum value if it is in the left side, and what do? We replace it with the in order successor, then delete that particular root. So that is what. So find the successor of the node. So node successor, we have created one node as successor, then it is equal to the root, right? And if it is not null, this successor is not null, then parent is, that is what, it is pushed. This is compared and the root node is pushed. The successor node, the new node will be pushed to that particular parent, and the parent will be deleted. So that is deleting the successor when the node has two children. Okay. Next part is searching. This is one more important operation of binary search tree. So searching for a key element inside a binary search tree. So we know that binary search tree will have, it's an order, it has a unique order, and every element has a unique value, and the left side subtree is always lesser than the root, and root is always lesser than the right subtree. So if at all, so it's an algorithm says like this, if root is equal to null or root data is equal to key. That means if there is only one element, the key element you want to search is there in the root, you are going to return that particular node. Only one node is being returned. If the key, root key is less than, if the key element is less than root. So the key element is left, then whatever element I am searching, if it is less than the root key, what I am going to do, I am going to search the element in the left subtree. If it is greater, I am going to search that element in the right subtree. That is what searching. So see, in implementation, that is what they are telling. We are creating a node as search, then root, then inserting the key element whichever you want to search. Then I am checking the condition if root is equal to null, and if that root data, whatever data I am searching is equal to key, the whichever element which is there in the root is equal to key, I am going to return the root. If key is greater than the root's data, so whatever data is there in the root which is less than the key element, I am going to search in the, sorry, this is actually, if it is less than key, I am going to search in the left part. If it is greater than key, I am going to search, it is greater than the root data, I am going to search in the right part. If it is smaller than the root data, I am going to search in the left part. So this is, see here, with the example, if you want to see, there is what tree here. If you want to search a key with the value 6, 6 is where here. So in the about tree, then you first compare the key with the root node. So I am comparing this element. So I want to search for this element. I am comparing this element with the root. So if it is lesser than 6 is lesser than 7, so I don't go to the right subtree. I will just avoid going to the right subtree, and I will only search the element here because it is lesser. Just because it is lesser than the root node, it is there in the left subtree. So this condition is false. Now next we descend to the left subtree. Again this is compared with the root. Now root, what is happening? This element is greater than the root. That is why I won't search in the left. I will be searching the element in the right side. So I will be saying if 6 is less than 5, no. 6 is greater than 5 and we have to move rightwards. So 6 is equal to 6. Then the key is found. Okay. Even in binary search tree we have traversal operation just like binary tree. Same thing, in order traversal, pre-order traversal, then post-order traversal. You know what is in order traversal, we've already gone through that. In order traversal is you're visiting the left subtree, then the root, and after that we'll be traversing to the right subtree. Pre-order traversal is we visit the first, we visit the, pre-order is we're visiting the left side, then root, then the left, first we visit the node, then traverse to the right subtree and left subtree. This is root, this is, okay, this is left, it's not writing, okay, this is, so let's see here. So if it is in order, what is happening in order? First you are going to visit to the left subtree, then you are going to process the data inside the root. After that you are going to visit to the root right side, right subtree. If it is pre-order, you are going to visit the root data. First data is visited, then first the root is visited, then the left subtree is visited, then the right subtree is visited. So if it is post-order, first the left subtree is visited, then the right subtree is visited, then the root data is processed. This is similar to that of a binary tree. So I think you know what is the difference between the binary tree and the binary search tree by now. So it is very easier. So these are some applications of trees in data structures, that is binary search tree applications. The first is, in binary search tree it is used to check whether elements are present or not. Okay, it is easy whether if you identify some element which is there inside a tree or not. So heap is a type of tree that is used to heap sort. The third application is tries are the modified version of the tree used in modern routing. This is tries actually. This is one application which is used for modern routing. So I told in the morning, so binary search trees are used for routing algorithm. So this is tries. This is one sort of application. It's a modified version of tree. Okay, it is used for modern routing to information of the router, to gather the information of the router. So it is used in databases, usually B tree. There are other type of trees is not there in your syllabus, like we have EVL tree, red black tree, B tree. So this B tree is used in database. Okay, then compilers use syntax trees to check every syntax of a program. Then you have come to end of this tutorial. That is what. So by this we'll be ending this session. Thank you so much.